This is Josh Mendenhall, and this is a demonstration on using Grasshopper and the Ivy plugin to sort of 2D lay out a mesh and any mesh of your choice. And we'll go from this just simple chess piece, simplified mesh that I have, and show you how to get these planes, like these pieces, laid out in a grid. So if you were to apply a subtractive manufacturing process like CNC milling or laser cutting, you could take this and cut these pieces out and apply and reassemble these pieces to develop this 3D mesh, this 3D form in real life. The one drawback to this is the more complex your message, the more pieces you are. So I went with a pretty middle of the ground mesh in terms of face counts. So I reduced it quite a bit to get to the point where it's at. But if you are okay with having a lot of 2D like pieces laying out on a large grid, then you wouldn't have to reduce your mesh as much. To start out, you first want to go to Food for Rhino online and download this Ivy plugin. And something that was really helpful for me to do this to develop this script to be able to do this was using this example set, which comes with different scripts, and you can apply them as you see fit into your own script to get the desired 2D layout as you want. So to start off, we can break down the script and how we went from step by step to get to this final point. So you'll want to start out with your desired mesh that you have, your 3D form, and in Rhino 7 or whatever version you're using. And you want to apply this. Hold on, I'll turn the final product off so we can get there. So here, I'll hide this as well. So once I assign that mesh using set1 mesh here, that's when you'll first get into using Ivy. So the first thing you want to do is create a three-dimensional graph of this mesh form, and you can do that using this graph from mesh command in Ivy. It can be found in, you'll go up to this first tab and you'll find graph from mesh here, and this pretty much is what it says, creates a three-dimensional graph of that mesh form, and you want to add weight to these lines. So you'll go up to the weight graph and select, you'll select the face angle edge weight component, and that just adds weight to this graph so they're not just unweighted lines. It actually, like, you can use them and scale them down and two-dimensionally lay them down. So from there, you want to create a tree-based mesh form, or tree based on the mesh form. So you'll go up to the primary segmentation tab and select the MST cruise call. So like it says here, it just computes the minimum spanning tree of the mesh using the modified cruise calls algorithm. And this is what it looks like on the left here once you apply that and plug that component into so you're going from graph to graph here, and from like before, you'll go from mesh to graph to graph to graph, and so on. So, so you want to now move into sort of unrolling these components, and how you're going to do that is use the mesh graph unroll component. So you can find that in the special segmentation tab up here, the sixth one, it is called mesh graph unroll. So you're going from your tree-based tree based on the mesh form, still graph format into another graph here with it, which is just unrolled out onto the 2D plane, two-dimensional plane. So from there, you will create this flat fabrication data. So what this is going to be developing the actual like pieces of like those two-dimensional pieces that you see that can be reassembled together. So it takes the information from this graph and kind of puts them into 2D pieces that can be put together. And you want these flat pieces to have flaps on the end. So like if you were taking this origami, like this paper folding approach, you would have paper flaps on the edge that would hold the pieces together. So what this component does is glue flaps and creates glue flaps and allows them to create like be selectively created for like the corresponding edges that they need to be, and you can like set the width and bevel for each of these and how this is plugged in. So your like mesh edge index, this this edge type command extracts the mesh edges and identifies them as graph edges and cuts out the ones that like you don't need. So it takes that graph data and kind of cleans it up, and so it doesn't just create a bunch of random flaps, and it identifies which are graph edges and which are cut edges and which are like naked edges that you don't need. So like, and it knows where to apply the flaps as necessary. So the big thing about this flap fabrication tool is that this component is that the output, you have to have some sort of it outputting into something. It doesn't just automatically display what you want to see like those. So you have to take the cut lines that are like from the tree that it was unrolled out to, these cut lines, and then you'll have the inside fold lines, the outside fold lines, and then the flat lines. And you will sort of move them into curves, like apply them into curves so you can see them. So here we're seeing all of these different line types going into these curves. So they're all kind of laying out on each other. And that's probably the biggest thing about this. That's the most difficult thing about this concept of laying them out. Like you can lay them out easily onto this 2D plane, but they're all on top of each other and all kind of like it's difficult to follow. So the biggest breakthrough you want here is to I watched a lot of videos, and on the examples page, like you can download these example sets. So they have different files to like what you can apply into what you want to use. And from one of those files is this cluster that takes all of these flat two-dimensional pieces and lays them out as necessary. So if you were to apply them to laser cut, you could set them up in coordinates and like cut them as necessary. So what this does is you're pretty much establishing with the X and the row number sliders, and when you plug them in here, so this is just saying how you want them to fall on the XY plane, and the rows is like how many you want. So if I increase the number of rows, then obviously you're gonna have them all laid out in a single file with the maximum number of rows, but as however many you see fit, but it'll be in a column if you keep going up. And then, so if I want 4 rows, how it'll look, or 6 rows, I mean. And this just kind of, this scale here scales it down in the XY coordinate plane, so if you want them to be smaller or larger, you can lay them out as you see fit. So that's like the first part of this cluster, and then you're going to take the data that's outputted directly from this flat fabrication component and the curves that they're input into, and output them from the curves and write into this cluster, to this like piece arrangement. So the cuts are going to correspond to the cuts, the inside, outside, and flat lines are like the lines are all going to correspond as necessary, and then the placeholders are also going to just directly, like, you'll forgo the curve for that assignment and you'll just go straight into the placeholder input on this cluster. And the final thing that you need to input for this cluster is it needs to know like there's a graph for it. So you're going to use the flat graph, like the split flat graph from the mesh graph unroll component, because that'll output, it'll be the same exact. You need to specify what kind of graph you're going to use on that plane. So it's just going to take this output and use that as the same graph input on this cluster. And so that gives you, it seems like a lot here. So you have all of these graphs here, and you need to same thing, it won't automatically output the data that you want. So you need to then apply them directly to these curves, just corresponding. So like same thing as before, the cuts will be put into a curve, the inside folds will be put into a curve, the outside folds and the flat lines will be inputted directly into a another curve. So that gives you these 2D pieces that are now arranged like evenly among this 2D plane grid. And finally, the biggest thing you want to know is like coordinate wise how to like see this unrolled data. So you want to create a tag on each one that shows how you can, it'll show the unrolled data on these planes, on these pieces. So you'll just use a 3D text tag, and so this position here will input directly to the location on this tag. So tell it the location that you want to see, and then not all of the like branches are like how you don't have access to all the branches. So this shift paths component just takes in the tree text from the flat fabrication component, and we'll just take the data and put it right into the text tag here, and it like allows you access to all of the tree branch components. And then finally, you want to be able to adjust the size of these text tags. So here we can put on that we can see them. Oh. So when I apply that, you can now see that there are these numbers that correspond with the unrolled data. So if I want to increase the size of them or decrease the size of them, you can do it as you see fit with this number slider corresponding to what size you want. And yeah, so that is how you will go from this mesh, 3D mesh form in Rhino and take that mesh form and apply them to this Grasshopper script and be able to lay out these pieces. So if I were now to, like I said, take these pieces and put them on a coordinate and laser cut them, or take them through CNC milling or whatever, like you can now, once you cut them, these pieces, they have the corresponding folds and flaps that you need on the external cut lines, and you can piece together per the coordinate leg numbers and roll data and piece together this 3D form in real life. So this takes the concept of this paper folding or in origami, and you go from a three-dimensional shape in like a CAD software or in a 3D modeling software and take it into this CAD software or CAD format, and you have this computer-aided design, and you're able to bring that to real life through subtractive or additive manufacturing methods, and then reassemble it into a 3D real life format. But yeah, that is all. Thank you.